So welcome to our LibreHub seminar series. In this series, we present different open source projects in hardware that are geared towards microscopy and imaging in general. And we have a list that makes these seminars available. So I invite everyone to check our website and check our YouTube channel where these talks are posted. For today's seminar, we welcome Dr. Bryan Spring. He's an associate professor of biomedical physics and an affiliated faculty of bioengineering at Northeastern University in Boston. And he's also a visiting scientist at the Wellman Center for Photomedicine at the Mass General Hospital and Harvard Medical School. He's faculty at the Northeastern University, as he said. He joined in 2015. And since then, he has received the NCI Transition Career Development Award, as well as an award from the Smith Family Awards Program for Excellence in Biomedical Research. In 2021, he was selected as a Scialog Fellow for Advanced Bioimaging. Outside the laboratory, Professor Spring practices meditation and calisthenics. That's interesting. I don't think I ever heard what calisthenics is. So maybe in another time, I'll ask you more details. So,
sure.
Thank you very much for joining us. And so this seminar is funded by the Chan Zuckerberg Initiative, as well as this the same as this Scialog fellowship that Bryan has. So that's an interesting coincidence. And also, I should mention that we originally met at the Wellman Center, where we both worked at different times. So that was an interesting connection that facilitated this invitation. Thank you very much, Bryan. And so today, Dr. Spring will be talking about the development of an open source femtosecond fiber laser system for multiphoton microscopy. I'll give you the screen sharing here.
Yeah, thank you. Let's see. Okay.
Yeah, I can see your.
Be good. Yeah.
Yes. Now I can see the shared slide. Great.
Perfect. Okay. Yeah. Thank you so much for the invitation. And yeah, it is serendipitous how we ran into each other several times and realized we were both at Wellman and trained there. Yeah, and it's really a pleasure to be here. So I'm going to talk about a femtosecond fiber laser that my lab built. And to be humble about it, I never really intended to build a femtosecond laser. So this is a good test case because I don't have a formal training in laser physics. And kind of what happened here is I hired a postdoc and he was really interested. He came with a lot of fiber optics background. He was interested in bioimaging. For a postdoc, he was switching fields. And we got to brainstorming and we found some papers in the biomedical optics community about making your own femtosecond laser. And we're like, oh, wow, you can make one for really low cost. The price tag was very low, and that was appealing to me. I was starting a new lab. I didn't have a lot of money to spend. I already have a very expensive photomedicine program. That's one of my passions. So getting a femtosecond laser was kind of outside my startup package. We got to talking, we got really interested in this. And I'll tell you the story, and kind of the message of the talk is, if I can do it, you can do it. And we spent about 3 years on this. And I'll try to be really transparent about the cost and the intellectual investment, financial costs of all the equipment. It ends up being a lot more expensive than just the parts that I'll explain. But in the end, we're very happy about it because it gives us flexibility to kind of innovate our own laser. And we had help from laser physicists along the way. So I'm going to disclose that I'm not sure, it's not really relevant for this talk perhaps, but just to be safe, my photomedicine stuff has led to a company. So I'm a co-founder and have equity in that company, but there's no femtosecond lasers involved in that company at this time. And before I jump into this story, I'll tell you a little bit about my background in case it's interesting. So I started off as a physics major at Iowa State in the cornfields in the middle of the US. Did a study abroad in Valladolid, Spain, where my Spanish got pretty decent. I wouldn't say I'm fluent, but unfortunately I've forgotten a lot. He olvidado mucho. So I'll give this talk in English as standard for this. And then I got interested in biology. I kind of realized that being a string theorist or particle physicist would be highly competitive. And I got interested in biology through popular science. And I kind of heard that biophysics was an emerging field. So I switched to biophysics with the idea that there could be a career there, and it aligned with my interests. I had a lot of fun doing biophysics, and most of that was microscopy, like fluorescence lifetime and FRET, for any of you who are familiar. And then I found that was really exciting, but I wanted to do something more applied that could impact the world more directly, I thought. So anyway, I got interested in cancer through some of the biophysical microscopy and photomedicine. There was some overlap there. And I went to the Wellman Center, which is very strong in microscopy and biomedical optics, as well as this photomedicine component for cancer. And then I returned home. I had a big scramble at the Wellman Center to try to find a job after that. I had good mentorship to help me through that process. And I ended up finding a place at Northeastern in Boston. And it was kind of miraculous. That's kind of maybe a story for another day, like how I managed to get a faculty position in Boston. Was definitely a small miracle. So being back in the physics department, like I said, I recruited Nima, who's shown here, to my lab. And what we really did was we translated advanced laser physics to something that we think a biomedical optics person could do without a training in laser physics. And we really needed help to do that. So Frank Wise, shown here at Cornell, if you don't know who he is, he's wonderful. And he really developed femtosecond lasers. Actually, the original paper reporting multiphoton microscopy coming out of Cornell, Watt Webb's group. Frank is actually credited in that paper for developing the femtosecond laser that was used. And the technology has come a long way, and you can certainly buy a solid state femtosecond laser, which is probably the thing to do if you have a core facility. There's very powerful commercial systems that are very user-friendly. They kind of come in a big box, and you need to put them on a vibrationally isolated table. And for about $250,000 last time I checked, you can get a laser that's tunable will have an OPO on it that can tune the wavelength. And that's a great system. But if you're like me and you have a limited budget for your lab and you kind of want to learn about the laser and how it works and make your own, Frank's designs turn out to be very amenable to doing that. And I think they represent probably the lowest cost and easiest to fabricate designs that are out there. And what happened is Nima and I were reading papers, and we realized that Frank Wise's group had done a lot of great work. We were really impressed with his papers, and we reached out, and he responded to us, to our surprise, and was willing to help us and actually hold our hand through a lot of this. So the laser I'm going to present is a design that Frank developed a while ago. It's an older design, and it cost us about $13,000 in parts. And in the end, it produces about 200 milliwatts of power that you can send into a microscope, 70 femtosecond pulses. And we actually made two different repetition rates, which really depends on the length of the cavity. And we were successful with 30 megahertz and 70 megahertz. All right, and here's just a couple of pictures. This is what the gain fiber that's shown here. This ytterbium dope fiber, that's what that looks like through a infrared viewer. You can see it lighting up. And then here we have a microscope objective next to cuvette. You can see the point spread function that's being excited. You can see some fluorescence coming from the point, and that's indicates that we have multiphoton excitation. Okay. So the outline for the talk, what I'd like to do here, and by the way, feel free to jump in with questions at any point, real time, just speak up. and I'll stop and we can chat. I'd rather have a discussion than just talk at you. But what I want to do is try to share our journey with you in hopes it will help. And we spent a lot of time, that 3 years, and we put out 2 papers that I'll reference throughout this talk that I think are really helpful, hopefully, to explain exactly what we did. So I'll talk about how the pulse physics works to the best of my ability. Keep in mind, I'm not a laser physicist. I'll try to explain it. Then I'll talk about how we built it. I'll show a couple of videos in that process, short clips, and there's more video available that you can actually watch if you like. I'll actually show the parts list, but it's also available in the papers, so you can get access to it. The equipment list. So there's some equipment you need to actually fabricate this thing that's probably not around a typical biomedical optics lab, unless you're already doing fiber splicing. So I'll explain that. Then a really important part that was kind of missing in the translation that came before us. So other people in biomedical optics had tried to take the laser physicist papers and convert that to a laser in their lab. And a lot of the lasers were just not working properly, we found in the literature. So that was a little bit misleading and unfortunate. And I was really careful not to make anyone feel bad about that, because it was, innocent people were doing their best work, and I didn't want to embarrass anyone. And I myself struggled through this. So in any case, there's a lot of bad papers out there. And one of the problems is you have to make sure this thing's action mode locked, and that's not so easy. So it can be deceptive, and I'll try to explain that. That'll be kind of the meat of the talk once we get there. I'll make a few comments on how much this actually costs in dollars and time. Then time permitting, I'll wrap up with a new design, again, actually coming from Frank Wise's group. He's got something that came out in 2022 that's even more powerful and just as easy to put together as what I'm presenting today. And then, I'll talk a little bit about future applications in my lab, like why we built this and what we're excited about in case it's of interest. So these are the 2 papers we published with a lot of love and determination to try to share our journey. And again, it's not a novel laser, so it's kind of an interesting publication review process. The reviewers really didn't like it, but we kind of pushed through. And we've gotten a good reception in the community, gotten several emails from people who are interested in building this. We're trying to help them. But it's a really tough peer review process because there wasn't novelty. It's really just a translation of things that are known and to make them more accessible. So kind of in a new language, and spelled out more than normally the laser physics papers skip over a lot of things that you just wouldn't know unless you trained in the lab. So there's a scientific reports paper, and then there's a Journal of Visual Experiments, JOVE paper that has the video, and I think you have to pay to get that video, but we're going to try to make it available on my lab website very soon. So how does this thing work? It's what's called a dissipative soliton laser. Another name it goes by is all normal dispersion, or ANDI laser physics. And so again, it's a ring of fiber, and then there's some free space optics. And the free space optics are there because when you first build a fiber laser, you really want to start with something where you have full access to tune some of these parameters. If you try to build it all in fiber straight away, it's a much more challenging build in general, particularly with this laser physics here. So all of these components could be made into fiber component analogs, but that's just much more challenging. So we started with the free space optics here, and then there's a ring of fiber. And it comes out with like a picosecond pulse here. The pulse is highly chirped. And then you have to use transmission gratings to correct some of the dispersion and put the wavelengths back together. They're kind of spread out from red to blue. Wavelength shifted in the pulse, and then you can kind of recompress the pulse and send it off to the microscope. And that's where it gets down to 70 femtoseconds. So how this works in brief is, let me back up for a second. So you have a continuous wave pump, that's coming in to the fiber ring, and it's coupled to the cladding. So we pump the cladding of a ytterbium dope gain fiber, and then the pulse forms and moves around the laser. And so to go from continuous wave lasing to a femtosecond pulse, you have to do some pulse shaping in the oscillator. And one principle is satural absorption. And an interesting thing about this wave that I think is very elegant is the satural absorber is actually the combination of wave plates and a polarizer. So often people will have a material that undergoes the Kerr effect. So basically, you only pass very intense light, and you start this thing from fluctuations in the system. So you turn it on, and then there's fluctuations, and some of the fluctuations are very intense pulses of light. And then there's weaker pulses, and you hear what's happening as you're filtering out the weak pulses and focusing in on one very intense pulse. And that's the laser, and this happens within a very short period of time, less than a second probably. And then you get this pulse moving through the satural absorber. And the way it works is that part of this is that there's nonlinear polarization evolution in this design. So this is non-polarization maintaining fiber. And as the intense pulses are actually able to move in polarization, and they can make it through this satural absorber. Then the second part of this is that there's each cycle after the pulse picks up gain, it spreads out in frequency due to nonlinear effects and dispersion and the glass of the fiber. So each cycle through, you have to have a spectral filter that kind of chops the pulse. So it chops off the red and blue wings of the wavelength spectrum of the pulse, which also happen to be spread in time. So you're shaping the pulse in both frequency or wavelength and time with this spectral filter. So it kind of resets the pulse each time, and it goes back through the gain fiber. So hopefully that gives you a picture, and I have one more slide that will illustrate that from Frank's lab. Before I get to that, a unique feature of this design is that you can have very high pulse energy within the oscillator itself, and that makes it distinct from a lot of other femtosecond fiber laser designs. Many others have a very low pulse energy inside the oscillator, and then you amplify it in 1, 2, or 3 stages. Once you come out of the oscillator and you've created a femtosecond pulse, you then amplify to get to energies that are useful for microscopy. So this is 1 to 2 orders of magnitude larger than a normal soliton. So this I pulled from Frank's website.
Bryan,
so if you go to the yeah, question.
Can I ask already? What are the pros and cons of this later amplification? So is it? I assume it's simpler and cheaper not to do this later amplification.
Yeah, great question. So from my perspective, I'm trying to reduce the number of parts and things to be built. So getting more power out of the oscillator makes it less expensive, because each time you amplify, you need some more pump laser power. So that could mean that you need to buy a second pump or a third pump, and each one is, $6,000 to $8,000 roughly. Last time I checked, at least. Yeah, so it's to reduce costs. But on the other hand, if you need a lot of power, it's not a bad way to go. If you're doing something special where you're going to need to amplify anyway, if you need more power than 200 milliwatts, then yeah. So yeah, there's a lot of trade-offs here, like with all optics. There's no clean answer. So a great question. But we liked it to start because we didn't have to build an amplifier. Not the amplifiers are hard, it just adds cost. All right. So this is a beautiful little cartoon schematic video from the WISE research group. So I left the link here at the bottom of the slide, and there's a lot of resources there. There's other pulse physics that are described, and it's a great resource to understand this. So this is the Andy, and it's just what I said. And what you're actually seeing here on the left is a simulation. So Frank's group, they actually designed the laser physics by simulating in part and thinking on paper too. And they have a nonlinear Schrodinger equation, and they put in all these different parts of the laser. And it's really complicated. These ring oscillators can do a lot of different things, and one of the things they can do is produce a femtosecond pulse, as Frank says. So there's a few configurations where you actually get a femtosecond pulse out of the entire space. And so one thing I would say is, if you tried to build one of these, I would just copy my paper directly and not try to do anything new until you know what you're doing, because you change one little thing, one component, and it can change the pulse shaping, and you can lose the mode lock and the ability to make a femtosecond pulse. So what's happening here on the left is you're seeing a simulation, and you have, this is the pulse, and this is kind of the pulse spread out in time. And remember, it's highly chirped, so it grows picoseconds in the oscillator. And then this is the wavelength. And then here you can see the wavelength spectrum plotted, and here you can see the intensity spread in time. And the simulation is following this red dot. So this is the pulse moving through. As you can see here, it's going through the spectral filter right now, and here's a spectral filter being applied, and that chops down the edges of the pulse in time and in wavelength. And that keeps resetting the pulse. And then as it goes through the gain fiber, it grows in intensity, and it picks up these non-linearities, and you get this characteristic cat ear spectrum, or Batman, where you have these ear-like shapes, these sharp features, and that's from the non-linearity. After you pick up the gain, you have this high non-linearity and self-phase modulation in the fiber that gives it this funny shape. But if you don't have that cat ear shape, is one of the hallmarks that you actually have a mode lock. So when Frank and I looked at some of the biomedical optics folks who tried to build this laser, they did not have the cat ear spectrum, and that clued us that something was wrong. Okay, so hopefully that's helpful. And here's again the specifications that we achieved. So we have the cat ear spectrum. We did a simulation also for our fiber using Frank's software, and the experiment comes out pretty close, which is remarkable considering how complex this thing is. And there's a lot of approximations and estimations made because you don't, well, and it is such a complicated system. So we get the cat ear spectrum. It's a spread out from about 1060 to 1080. You really have two peaks that you're working with. And then the pulse width is about 70 femtoseconds if you really work at it. And then an important thing is like, how stable is this thing? So it's really remarkably stable. So this is these are 2 runs for 24 hours. Now the thing is, you can't touch it. Okay, I know that sounds silly, but if you come in and poke this fiber during an experiment, or you bump it, you'll lose the mode lock potentially. And that's because all this fiber is not polarization maintaining. So when you bump it, you change like mechanical stress in the fiber, and that changes the polarization evolution. And then you'll have to go back and adjust the wave plates. Now it's not too hard once you get good at it. Initially, it can be a little bit of a struggle to find the mode lock, but once you find the mode lock, and then if you bump it and lose it, it's pretty quick to get it back. So that's just a disclosure, so you know it's one of the quirks of this particular laser design. And again, I said we achieved 2 different repetition rates, if that's important to you. Typically, when you buy a commercial laser, everything's 80 megahertz, and that's just because there's no real reason for that. It's just a number that people have stuck to. And here we literally cut the fiber shorter and then respliced it to get 70 megahertz, and it still worked. If we tried to push the frequency repetition rate higher, the pulse physics started to fall apart. So it started to not work so well. And if you're going to build this, I would recommend starting with 30 megahertz, because that's a nice zone where it's pretty robust.
One quick question, Bryan. So
Yeah.
When you change the, well, I understand it's not easy to change, but when you make the fiber shorter to make it 30 megahertz, do you have the same average power or the same
Good question.
energy per pulse?
I think the pulses came out about the same. They're a little bit different, but they were still less than 100 femtosecond, they were still nearish to 70 femtosecond and still about the same power. Yeah, so it doesn't affect the power or the pulse duration too much. Yeah. Why that is, I'm not sure. But, okay, so how to build it. So, I mean, I'm not going to read you the parts list, but here literally is the parts list that's in the paper and the supplement. If you download the supplement of the scientific reports paper. And so we tried to put enough information that you could easily find all these parts online, and we list the price. We were pretty obsessed with the low cost. We thought that was really compelling. I don't know how compelling it is to other people, but for us, it was really important. And we tried to get some details for each of these that are helpful so you know exactly what we got. And we provide like the mode field diameter for the different components. And that's important for the splicing. So there's a lot of details that we put in here that hopefully helps. And again, here's this warning. We had a lot of guidance from Frank on what parts to buy. And then we found a new ytterbium gain fiber that had a huge gain compared to what Frank had used. And we thought, oh, we're going to modify this and make it even, higher power. Let's see if we can get, 3 watts out of this cavity. And that was a bad idea. We ended up wasting probably 6 months just melting the fiber and burning it. So these things can get hot. There's little tricks. Anytime you put any splice junctions where you splice 2 fibers together, like here, there's 2 different fibers that are slightly different size. You're going to have some light escape and potentially heat stuff up. So you kind of put some coating on there. You put some it's like a glue that you stick on to these joints that helps the light escape and helps keep things cooler. So we do that. We talk about that in the paper. But it's just something to be aware of. So that's just an example where you try to modify it and things can go wrong. So that was frustrating for us. And we ended up going back to kind of what Frank was using in the end, after struggling for several months. Now, here's the reality of it. It's not really $13,000 in parts because we also needed to have access to fiber splicing equipment. And for us, we needed to go out and buy equipment. And we chose to buy new equipment. You can buy refurbished stuff if you want to save a little bit of money. But these splicers have a lifetime. They wear out over time. So we decided to buy new. And, it's about $38,000 US dollars. So but here's all the information. And we're really happy with the splicer. It works great. We've had no issues with it. You also have to buy a cleaver to cut fiber. You want to make really nice cuts. So you need a device that holds it and cuts it precisely. So I'm gonna
That's
stop
really
talking.
Crazy. Can you comment on that a little bit? I mean, I haven't done fiber splicing. I don't really know what it's about.
Yeah.
But this seems to be like a really significant cost. And does it have to be done like very fresh or so? Let's say, could you cut the fiber and send it to us, kind of thing, or
Yeah.
what's the deal with these machines?
Yeah. No, it is expensive. I was disappointed when I found out how much it was. Yeah, and thinking about an open source platform, like if I'm totally open to collaboration and to input from you all, like what's useful. But maybe that's a model where there's a fiber splicer that someone owns, could be us, who just provides the splices, and like it could become like a kit where you just provide this, or you actually assemble the ring oscillator part way and then ship it out. And I don't think that would be, I think it'd be very shippable. I think you could protect it so it wouldn't break. I don't think it's that fragile, but definitely you would have to handle it kind of carefully to make sure you don't snap it or something. But I think what I'm trying to say is it's fairly robust. I think it could be spliced somewhere and then shipped out.
But in principle, you make one fiber and then you keep using it. You don't have to redo this now and then.
Yeah. Once you have a working laser, it's highly manufacturable, and shippable and all that. And in fact, this design, I should say, KM Labs has commercialized it and licensed the patent from Frank. And I believe the laser's even sold on Thor Labs now. I think they integrated with Thor Labs. So yeah. Yeah. Yeah, keep the ideas coming. Yeah, I think there's ways that that could be done. That would be really fun. I'd be interested to try to help establish that. Let me show a quick video that will just, I'm not going to show a very long clip, but you'll kind of hear the narrator from the Jove article and my student Kai Zhang here working on a splicer, so you can kind of see the process.
The two fibers to be spliced together should have cleaved ends opposing each other by the fiber holders within the fiber splicer. Close the cover of the splicer and set parameters such as core diameter, mode field diameter, and cladding diameter. Set the alignment method to cladding, press the Set button, and the splicer will align automatically. Press the Set button at every stop to confirm the quality of the alignment. The splice will be done automatically. Check the quality of the splice using the quality controls of the splicer as well as the camera view of the region.
Okay, so that's it. So once you know what you're doing, it's really just using this machine. You can see how beautiful that splice was. And one note I should make on this is that because we're doing the cladding pumping and having the high pulse energy in the oscillator, it turns out we need to splice dissimilar fibers together. So I'll try to show this in another slide, but there's several different fibers we're putting together that we put a lot of thought behind in selecting them. And they all have different mode field diameters. They're slightly different dimensions. And you need an expensive splicer like this to put the similar components together. Now, if you did a lower energy pulse, there's another paper that I cite in the scientific reports paper by Tom Allison at SUNY New York, who's a laser physicist. And he built a beautiful Andy laser using a really cheap splicer. So there are, if you're just doing certain type of splices that are simpler than what we're doing here, you can buy something super cheap.
And
Maybe
a quick note, Brian, can you comment quickly on the, so I assume it's not possible to just use connectorized fibers, right? Can you explain why?
Oh yeah, that's a great question. I have a feeling that you'll get too much leakage, or I would worry that that the connection just won't be solid enough. Like here, you have to have a really low loss percentage, like 0.03 dB or less. I don't know how well those connectors work. So, you know, I would suspect that the fusion, actually melting the glass together, fusing the glass together, gives you the lowest loss possible. And any loss you have will cause reflections in the oscillator and disturb the mode lock. That's probably the big thing. You have any reflection that's significant, and that will disturb the mode locking, and you won't get a mode lock. So that's what I think. To the best of my knowledge there. Okay, so once you splice it together, which will take some learning, I was lucky to have a postdoc who was like an expert in splicing, but he was able to teach my lab members who continue to do this today without any issues. Then the next step is how to find the mode lock. And we're going to dive down a little bit, but here you need some more equipment, unfortunately. You need to actually do some pulse diagnostics. So we tried to be as economical as possible about this. We bought some used and refurbished equipment to save money on the optical spectrum analyzer, which can cost $30,000 new, but they work perfectly well refurbished. We got a fancy oscilloscope on the cheap that was used. And in the US, there's these companies that refurbish equipment and you can find them pretty easily. And I've listed them here. So that's kind of the story there. And I'll show another quick video about how you get the mode lock.
Turn on the oscilloscope and set the instrument to AC coupling mode with the trigger level set to 30 millivolts. Move the optical spectrum analyzer photodiode input fiber to monochromatic input and set the device to OSA mode. Then, lock the phase of the laser by adjusting the wave plates. Rotate quarter wave plate 2 several degrees back and forth. The mode locking spectrum consists of 2 stable peaks with a plateau between them. Meanwhile, observe a stable pulse train on the oscilloscope. If the mode locking spectrum is not observed, rotate quarter wave plate 1 several degrees in one direction and repeat the previous step. If the spectrum is still not observed, rotate the birefringent filter several degrees and repeat the process.
Okay.
Mode.
So you're really playing with the wave plates, and there's kind of a systematic way to do that. So these are the wave plates that are in the free space. And I think there's 3 of them. And the nonlinear polarization evolution is happening. So you're trying to find an orientation where you're getting the big pulse through and getting it to go through the polarizing beam splitter. In really simple terms, oversimplifying it. That's kind of what you're doing there. Making sure the light twists in the right amount to get that big pulse through. There's another video that inspired us from Logan Wright, who's in Frank's lab. And he really was helpful. He was the point person in Frank's lab that kind of held our hand through all this. And he published a YouTube video that you can go look at that also describes this process. So, and I put the link here. So a couple of resources there to learn how to mode lock, but it's really just getting used to it and kind of, it's an optics parameter search. You just try to be systematic about it until you find the right conditions. And then once you find the right conditions, you write it down so you don't forget it. Okay, here is the major pitfall that we found in the literature, that there is this partial mode locking that looks like mode locking, but it's not really mode locking. I'll try to explain what I mean by that. So kind of going back to this pulse diagnostics, here's the equipment that you need to buy. And so you can send the output of the laser through a beam splitter and kind of get to all these different pieces of equipment. And there's a high-speed photodiode that couples to an oscilloscope and to a frequency spectrum analyzer. So the first thing you need is some kind of autocorrelator that will measure the pulse duration to see if you're getting femtosecond pulses. And this basically splits the beam into 2, and then the 2 beams are then autocorrelated onto a crystal, and you look at a second harmonic generation effect that you detect, and you kind of move the 2 beams on a delay line and overlap them and look at the autocorrelation at each point. And that gives you a sense of the pulse width with femtosecond precision. And so this is the 70 femtosecond pulse. Then we have an optical spectrum analyzer that you can use to monitor the pulse spectrum, which is really important. You want to have that on while you're actually trying to find the mode lock and you're looking for that cat ear spectrum. And then through the oscilloscope, you can look at the pulses coming through in time. It should look something like this, where you have, the 30 megahertz pulse repetition. You should see that. And you should see very low amplitude fluctuation if it's mode locked. And then finally, you do so like in this output, the pulse rate frequency coming through the oscilloscope, you can't really tell if there's higher order things happening at other frequencies. Your eye just kind of picks up the major frequency. And so it's really important to do this power spectrum and this RF frequency power spectrum analyzer. And here, ideally, you would get like an 80 dB, 70 to 80 dB single peak, and then have nothing else beating near that mode lock frequency. And so this will become more apparent as I show you cases where the laser is not operating properly, and you'll see how this behavior changes. So here is where we have a single pulse mode lock with the Batman or cat ear spectrum. We've got these nice regular pulses in the photodiode. And I'll show the other pulse diagnostics on the next slide. Here is an interesting phenomenon that happens in this Andy laser. So as you turn up the pump power, the pulses actually quantize, and they'll actually split into multiple pulses that are right next to each other. And so you get this multi-pulsing phenomenon. And so that's a way to increase the rep rate. We haven't played with that too much, but it's an interesting thing. And it's still mode lock, and the pulses just split up here, split up into 3 pulses. And that really happens at the higher power once you're above 1 watt coming out of the oscillator. So you're really pumping it hard. Now here is seemingly mode locked or partial mode locked mode that we've seen in the literature a lot. And it looks like here that you have a pulse spectrum that's kind of defined. But the thing is, what you have to remember is the optical spectrum analyzer is averaging over a bunch of pulses. So what's happening here is you probably have a bunch of different pulse shapes that are coming in time. Like each pulse is a little different and has sharp features, but on average you get this smeared out looking thing. So that's what's happening here. And there are ways where you can look at a single pulse and get away from the ensemble average and actually see that. So there are papers out there where people study noise and soliton physics, and you can see this actually happening. All right, so this is a really smeared out average, but if you look at the oscilloscope, it looks like a regular pulse train at 30 megahertz. So it looks very similar to the mode lock, and that can fool people. And you'll notice that if you look at a longer time for the pulse train, there's more fluctuations than when you have a mode lock, which you don't want this type of fluctuation when you're imaging for sure. Because then you won't have a true intensity map. Your intensity will be dependent on what was the power of the pulses that were coming in. Then
Bryan,
this is a little bit, yeah.
One question. So in this
Sure.
partially mode lock problem, so what's the problem with the laser operating this way? Is it that you have too much noise, or is it that the peak intensity is reduced dramatically, or something like that?
Yeah, good question. It's really too much noise. I think you don't have the full coherence of a true mode lock. So you still have some fluctuations, you still have some phase shifting. And it's really just now to answer your question, and I'll get to it in a few slides. It's a great question. You can still actually do multiphoton imaging with this partial mode lock, remarkably. But some of your pulses are picosecond, some are femtosecond, some are big pulses, some are weaker pulses. So it's just more variable. And you would have to dwell each pixel in order to kind of average out over the fluctuations and hope that there's no long-term instability. So it's just unstable, to answer your question, not ideal. Things get a little more wild if you tune to not mode locked. So what's happening here is something called Q switching. This is really noisy. So even more noisy than partial mode locking. So you're having lots of fluctuations, and you're getting Q switching where you're getting a buildup in the gain fiber, and then you're just dumping a huge pulse every once in a while. Then you have these little fluctuations around that. And that's not ideal. So you actually burn your sample. I'll show that in a minute. That's actually dangerous. You can actually burn your sample up. Before we get to that, just to finish this out, these are the other pulse diagnostics that I talked about. So here's the pulse duration, and here's the power spectrum. So when you have mode locking, you get a nice femtosecond pulse for your pulse duration. And when it's multi-pulsing, you actually start to autocorrelate with pulses that are nearby. Because remember, it got split up into neighboring pulses. So once you get out far enough in the delay, you start to see the other pulse. So that's why you have another peak here. For partial mode locking, you do have femtosecond pulses you can use to image, but you also have a lot of picosecond stuff happening, which is not ideal. And then for the Q switching, you have this kind of wild stuff happening here. This also shows up in the power spectrum where you see that it's not phase locked. So you have other frequencies happening outside of the peak, the major mode. And for not mode lock, it's really a wide range of frequencies are happening. Okay.
All right. Can I ask again?
Yeah.
This is really nice. So thanks. I'm learning a lot just for listening to you.
Yeah.
I'm just wondering, when you operate the laser, like once you tune these parameters and you switch it off, and then let's say a month later you come back to the lab, you switch it on, you have to double check all these things again, or you assume that this normally remains?
Yeah, great question. So I would say day to day, it's very stable. So if you're using it on a day-to-day basis, you're not going to have to do much tuning. And you can trust that it's the same as the day before. But, you know, as weeks go by, or if you leave it off for a while, you definitely want to check all of this. So in my group, we don't need to check all these diagnostics every day. But if we let it sit for a week or two, then we go back and make sure.
Okay. Okay, so that definitely means that you want to keep all this equipment nearby.
Yeah. And I mean, this is just adjusting wave plates, really. So, and usually, you know, once you get that first mode block, you're kind of over a hump where you don't have to do much, as long as you don't bump it too hard or break something. You really just
the alignment doesn't seem to be too tricky, but I mean, you need those fancy spectroscopes and analyzers on the shelf, right?
Yeah.
That's what I mean, you know, because I could borrow that, for example. But then if you need it now and then, it's not so practical. Okay.
Yeah, good point.
Just to understand how it would work.
Excellent point. Yeah, I got you now. Thanks for clarifying. Yeah, I think you're absolutely right on. You'd want to invest in that equipment. But if there's a group of people together in the same location, they could share that for sure. You could put it on a cart and move it around because you wouldn't need it all the time. Okay, so this kind of goes back to Vicente's question on the mode block versus the partial mode block. And one of the reasons it was so deceptive is even with partial mode blocking, you get a decent image if you image kind of slow. So you can see there's a little bit more noise here than the true mode block. And then when you have Q switching, you're getting wild fluctuations. So every once in a while you get pulses that are strong enough, and you see like a line of you get an image, and then sometimes it's dark. And if you just average the partial mode blocking, it starts to look pretty good. There's a little more background than the mode block. So the signal to background ratio isn't as good as the mode block. It's about half as good. So that's probably why it was so deceptive, and people struggled in the biomedical optics community initially with this. And here you can kind of see the relative intensity levels. So for mode blocking, this is like intensity by frame, average intensity as we take a video of frames. The mode blocking is the brightest, and partial mode blocking is about half as bright. So pretty good.
I really appreciate that you benchmarked all of this. That's really valuable.
Yeah, thanks. We had a lot of fun doing. And again, I think laser physicists might be completely bored by this because it's just trivial to them, but to us, it was very interesting. And here's some videos that I think are fun. So, and particularly the not mode locked. And again, here you have the cavity dumping with Q switching. So you get these really intense pulses that are actually destroying the sample. And it seemed like the sample was peeling off when I watched this live. So there might have even been some ablation going on. I don't know if it's like heating plus like plasma creation. When you get really intense short pulses, you can do femtosecond surgery, right? So you actually start peeling electrons off of molecules and creating a plasma. It's like multiphoton ionization. So anyway, something interesting here is happening that we don't want when we're imaging. So here's a summary before maybe I have a few minutes left, or we can stop. This is kind of a summary. So it was really a translation job, nothing novel about the laser physics, but just getting into the know-how that's usually hidden, kind of revealing that to make this all more accessible. It cost us about 3 years in time. We started from scratch. And remember, there's about a year of ordering parts or 6 months that you just can't get around. There's a lot of parts you need to gather, you know, and that's a huge time sink. And then there's a couple years or 2.5 years of just, you know, struggling through this. But we put a lot of that knowledge into the papers. So hopefully that time would be much shorter now. Especially if you asked us for help or we create like some kind of open source project, hopefully we could really cut that time down. So the total financial cost. So when I first, you know, read the papers in the biomedical optics community, I read, you know, you could build one of these for around $10,000 to $15,000. I got really inspired and excited by that. But it turns out it costs much more. So it costs $76,000 here in total parts and equipment. The postdoc is not included, by the way. So the postdoc salary or graduate student salary, whatever you have to pay, has a cost to it, right? And so I end up spending about $250,000. But to me, it was worth it. So I didn't know I was going to end up spending this much. But hopefully that cost will also go down now with our experience. That can cut down a bit, but to us, regardless, it was totally worth it because of the intellectual investment was worth it, and the growth that we gained in understanding these lasers, it was really valuable. And now we want to actually build on top of what we've learned to make some modifications. And by the way, all this stuff can be made to be portable because it's small. You don't need a big cooling unit. And once you have polarization maintaining fiber, you don't need even a vibration damped table. You could actually put this on a cart and go into the clinic, which also motivated us. All right, so Vicente, should I go on for a few more minutes, or should we stop for questions?
Yeah, we should be finishing soon, but go ahead and wrap it up, and then we can do a couple of questions.
Okay, all right. I'll wrap it up with the next few slides. I think this part's important. So before I stop, like the new designs since we published this paper. So this is going back to Frank Wise again. This is called the Mamyshev oscillator, and I think this laser is just awesome. So now it's all in fiber. It's all polarization maintaining fiber, so it's completely stable. You can actually heat this a bit. You can put it in a hot room and it will still mode lock. It's very tolerable of the environment. You can certainly put it on the cart and move it around. You can shake it, and it will still produce femtosecond pulses. The remarkable thing about it compared to the Andy laser beyond that stability is that it produces even higher energy. So it's 1.8 watts after you compress the pulse. So that's after the gratings and everything where you lose light. It produces like 2.5 watts out of the oscillator directly. Our laser that I showed you produces about 1 watt. You can push that up a little bit, but that's a pretty safe where you're not overheating stuff. So that's double the power. It's still got a pretty good rep rate and 80 nanojoule pulses with 40 femtosecond. So very short pulses. And if you know multiphoton microscopy, you know that the shorter the pulse, you know, the more like second harmonic and third harmonic generation you can get, and the more fluorescence. That increases all of those nonlinear signals to have the shorter pulse. And Frank's goal is to be able to image deep. He works a lot with Chris Zhu and Chris Schaefer at Cornell, and a lot of what they do is multiphoton imaging as deep as possible. So in tissue. So these are all great features for imaging deep. And then I won't have time to cover all this, unfortunately, but that's okay. But my lab is interested in hyperspectral microendoscopy. So I'll just kind of quickly skim through this, where we combine spectroscopy with imaging. So every pixel that we scan over, we collect a spectrum, and then we can unmix multiple dyes, which can correspond to multiple biomarkers in a tumor. And we want to image certain cancer cell populations that are drug resistant and immune cells, and try to guide photomedicine. And we're building a fiber scanning multiphoton system that images at 20 frames per second, because we want to image fast in vivo and image cancer cells and immune cells. And we actually want to be able to image them like moving and interacting and avoid motion artifacts. And we can't do hyperspectral multiphoton yet. That's a long story, but we're working on it. And the femtosecond laser and modifying that will help us to multiplex, and we need more excitation wavelengths, basically, is the short of it. So with that, I will stop and be happy to discuss things and answer any questions I can.
Thank you very much, Bryan. That's fascinating. So obviously I have a million questions about the microendoscopes, but just to focus down back to the topic of the talk. I guess I have so at least one very important question, because we have been learning more and more about open source hardware, and so this usually works best when projects are very cheap, and so people publish all the kits and instructions, and then like a DIY project, right? But here I wanted to understand better. So you mentioned that there is some intellectual property around this. Also, I think in the title of your talk, we wrote open hardware implementation, but then on the other hand, I think your paper, right, and or at least your research, you're not concentrated in emphasizing the open hardware part, right? So I just wonder, what's the IP situation around this, and can this really be built for free of intellectual property, or how does that work?
That's a great question. I shouldn't think about that. So we would need to check the patent and see if it is off patent. And that will be a key component, because I suppose that if we start an open hardware project and it violated that patent, that would be a real problem, right? So let me check on that and get back to you. It's possible that it's expired.
I mean, it's not so clear cut. I guess you can
yeah,
because if you build this yourself, it's not a commercial transaction. So in research labs, that's allowed. And then I guess you're still sharing valuable knowledge, and you can put a license on that. I guess you just have to be clear on what is yours to share and where do people need to be careful.
Okay.
Right. Yeah. So a key question, I think, is what is patented, right? Because I think it's broadly related to the principle of operation or something like this. But if you, let's say you publish, a way of building the kit or a parts list, that's probably not covered by the patent, right? Did you say there's a company that sells this design?
Yeah, there's a company that sells it called Cam Labs. I think they have a terrific product now available at Thor Labs. So that's definitely worth looking into as well. And I think it's much less expensive than a typical Thai sapphire laser, that runs 100,000. But yeah, no, I'm learning there too. Like, all of this intellectual property stuff is always, there's a lot to learn. Yeah, so I think we should follow up on that. And
yeah, no, my guess is that the patents prevent you from selling this, right, in a commercial application. But I'm not sure that prevents basically disseminating instructions on how to build your own, right? Well, I'm not sure. And then the technical question I had is that, So let's say for that product, right? So the company you said that sells this same design. So how does it work to make it like permanently stable? Because it doesn't mean that it
Yeah.
has like integrated all this diagnostic equipment and automatic adjustment, or
Yeah, great question.
how does it work more stably?
Yeah, but the answer is I don't know. It's a black box to me, but I imagine that they have, they've found a way to hold all the fiber in place, so that if you bump it by accident, nothing really moves. In my case, as you can see here in the bottom picture, we have just fiber loose on an optics table. But imagine if you pinned down, that would be my guess, that if you pinned it down, maybe you 3D printed some rails, or you had like the fiber like on a track or something. You could hold it nicely in place and you'd be more immune to vibration. So they must do something like that, but I'm not sure.
Great. So do we have any other questions from people who are connected online? We probably have time for.
Yeah, there were some things you were offering to talk about. I'd love to hear all the things you have to tell us. It's really exciting, that kind of work. I'm particularly interested in this kind of lasers at the moment because we would like to do some Raman microscopy application in a low-cost way, and it makes a lot of sense, all the things that you told me, because this is not just about having the laser but yeah, sort of all the equipment around it. Like it's about really making it work for someone in the biomedical imaging community. So a lot of those considerations are really interesting. There we also need the power and so on. So I don't know if you've thought about that kind of application. And then if you, I think you mentioned also in your abstract for the talk that you want to discuss a little bit the trade-offs between buying or building. I did mention it at some points, but in terms of sort of feasibility and cost and around the other equipment you need and so on, what are your thoughts?
Yeah, those are great questions. And I think it comes down to the individual lab, because you could buy a commercial femtosecond fiber laser. There's a few different designs, but it's going to depend on if the wavelength that you're interested in is available. And kind of like you were saying, if you go out and look commercially and you can find something for $50,000, let's say, which is a kind of a cost of a fiber femtosecond laser these days, I think. If you can find kind of the specs you're looking for, that's kind of a no-brainer. You just go get that, or maybe even 100,000 solid state laser, or 250K. Definitely for a core facility, you want maximum flexibility and usability, like out of the box. Then you definitely want to get the solid state laser with all the bells and whistles and tunability. Like this is not wavelength tunable right now. So those are some of the trade-offs. Now, I think if you go and you look and just can't quite find what you want, then making a custom system starts to become enabling for the science. And and if you're even willing, like in my case, I'm willing to even try to do wavelength broadening, and really get even deeper into the physics. And that's hard to find out there commercially for a fiber laser. So that all that together led me to just want to build this thing custom. I think you kind of have to look at what your application is and the growth of the application in the future. Would you outgrow a commercial laser quickly and want to do things on top of that? Those are some of the questions I would ask as you try to figure out what you want to do.
I think, I mean, in these systems, for me, cost is a particularly important component. So it's not the same at all for me, at least with sort of grant possibilities in Chile, if it costs $50,000 or $250,000. Like, I haven't heard of many grants that exist in the world that you can get from Chile that has this kind of money. You know what I mean?
Yeah, no, that's true.
Yeah, maybe you can get an equipment grant, particularly for that, but then it's also tricky because you can't so easily share it with a ton of people. So
Yeah, you're right.
I think that the cost reduction is a big point,
Yeah,
even if it's more effort.
Right. That's true. I totally agree. That was part of my calculus too. So thanks for saying that. And I think you made a great point there that typically if you're going to buy a laser like this, if it's not in your startup package, if the university hasn't given you money to buy it for your lab, then you're looking at an equipment grant. This is how it works in the US, at least. You apply to the federal government for an equipment grant. But yeah, like you said, you need to have a whole consortium of investigators who want to share it. And they're not going to give you $250,000 for your lab to buy a piece of equipment. It has to be a whole community that shares it. And then you're not able to modify it because it comes with a service warranty and someone runs a facility. And in my experience, they're not going to let you touch it for a good reason, because if you break it, then the whole instrument's down for the community. So yeah, that's totally true. The lower cost and then being able to actually play with it and to modify it to your needs. That's huge value.
Very nice. Yeah, it sounds like the at the end, I think the big barrier is the expertise and or the personnel, basically, to get trained on all of this, and that's a very important aspect also, because you can go there's low cost or low funding takes you part of the way, but then if you need to do stuff that you have to learn for a year or try for a year, that's also a huge cost in terms of personnel. But I think that's the beauty of places like Bryan's lab now, or in the Wellman Center, that they have like a lot of expertise, right? And so they just make new lasers for whatever application they need.
Right.
Very cool.
No, that's all true. I think, I would say, like, I openly invite you all to engage with my lab if you want to build one of these. And I'd be interested to do open hardware, assuming the IP is as we think, and we're free to do that. I'd be interested in a project like that, trying to support that, and have people could come visit my lab or maybe train virtually. I think now that we've published the papers and have the knowledge of translating it once, it should be faster to translate a second time. So maybe rather than 2.5 years, it could be a couple months of just like training people. And one question would be, could we train people virtually, or would they have to come to the lab to actually see in person? I don't know the answer to that. So that would be an interesting thing to investigate.
Yeah. Fascinating.
Yeah. Thank you so much for sharing.
Yeah. Thanks a lot
thanks
for joining us, Bryan. And this has been a great topic to cover. And so we'll post the video online and share it later on.
Thanks
a lot.
Right. Thanks so much.
Bryan,
take care.
Could I talk to you 5 minutes after the seminar? I would love to have another follow-up question. Okay, but then that's it for the seminar. Thanks.
Yeah.
Yeah, I'll stay on.
So I'm just